Good morning, Turav. Let me remind you what we did last week. Actually, we started our lecture 8, which is the second big title for constraint optimization. In the constraint optimization, we will cover two subtitle in lecture 8. The first subtitle with problems with equality and inequality constraint. Especially we focus on inequality part because in subtitle 1 we cover Lagrange condition with equality constraint, and then last week we covered what we do with inequality constraint. The answer was KKT conditions, Karışkan-Tucker conditions, to convert a constraint problem into an unconstrained one. We covered this one last week. We didn't cover non-negativity constraints. Non-negativity constraints is special constraints we frequently face in the application. So we will cover this special case, and after that, actually, we will cover all the topics. So we will solve some problems as the final course. Today will be our final course, I think. Next week, actually, in this, what was the time? The time is 10 and a half is enough for us. 10:30. Your makeup exam will be held. Okay, your makeup exam. Um, by based on the total number of the students, I will also announce the classroom. Okay, I don't know which classroom I will use because, as you know, this is an online class. But this is the makeup exam date. As you know, in the makeup exams, if you're taking your makeup exam from the first midterm or second midterm, again, all the topics covered will be content of the exam. So there is no separation for midterm 1 and midterm 2. So we will have our makeup exam, and this will be our first final class. Okay. So anyway, in the KKT, Karışkan-Tucker multipliers, we say that we have some equality and also we have inequality. We say that we discuss the active constraint concept, and we discuss active constraint set JX star. And for the first order conditions, we just write our Lagrangian by the summation of our objective function, lambda times the equality constraints plus mu times the inequality constraints. And we say that these are automatically zero from the equality constraint, and we assume that this part must be zero. So each mu j, gj multiplication, Karışkan-Tucker multipliers times the inequality constraints must be zero. Then LNF will behave similarly. So we can use L to find the extremizers of the function f. This was the first order necessary condition. This is the stationary condition, original equality, original inequality. This is the complementary constraint that we call for inequalities only. And also by the definition, mu j, don't forget that inequality constraints will be written in the form of less than. If it is greater than, you need to convert it into less than by multiplying by -1. Anyway, this is the assumption we use for mu. As you see from the constraints, there is no restricted value for lambda. Lambda can be negative, positive, or zero. It's free, okay? So anyway, we have n plus n equations to solve n plus n unknowns. And for the second order, we write nabla square Lxx. Xx means that actually with respect to x, we are writing the nabla square L. We are just investigating the positive definiteness, actually definiteness of it. If it is positive definite, it will be strict minimizer. If it is positive semi, it will be just a minimizer. If it is negative definite, it will be strict maximizer and maximizer similarly. We just solved this question last week. And we are now in non-negativity constraints part, okay? Today we will cover, this is a new part. This was just a summary before previous part was just a summary for you. Here we will discuss problems with non-negativity constraints. We face with non-negativity constraints in many industrial problem or engineering problems very frequently, so it will be worth it to analyze this special situation, okay? Consider the problem minimizing f of x subject to xi is greater than equal to 0. We assume that again it's a constraint, unconstrained problem, but non-negative constraints appear there. We assume f of x is continuously differentiable. We learned from the previous title that if we have a greater than equal to, we may convert it by multiplying it by -1. We will convert it into less than form. This is the case we need to do for in our theory. So anyway, you have a problem that matches with title 2. So all you need to do is applying Fontain's second order sufficient condition in title 2. Observe that your Lagrangian is objective function plus mu times gi of x. As you see, gi of x is defined as minus xi in this question, in this theory actually. So the gradient L, gradient F, this is the stationary condition, the first one. The derivative of this part, since gi of x is minus xi, the corresponding derivative will be actually -1, and we will use this simplification to analyze this theory deeply. Anyway, you can write, keep to write gradient gi, original constraints, complementary constraints, and non-negativity of the mu multipliers. So since gi of x is equal to minus xi, I can say that the derivative of this constraint with respect to xi is -1, while the derivative of minus xi with respect to xj, where j is different from I, the corresponding derivative will be 0. By using this simplification, we can write that actually dl over dxi will be df over dx in the component-wise form. Here it is component-wise form. Df over dxi minus mu I. Realize that we dropped the sigma notation here. We drop sigma. Why? Because we know that it is like that, mu1 times g1 plus mu2 times g2 and etc. If you take the gradient of it, it will be mu1 times the gradient g1, which is -1 or 0 in component wise, plus mu2 times gradient g2 and mu3 gradient g2. This is vectoral form. If you consider in component wise form, you will consider the first row as to write the derivative with respect to x1. Then this one will be -1, but the rest of them will be 0 for x1. For x2, this one will be -1, but the rest of them will be 0. So here you will keep the same idea, which shows you that actually for each xi derivative, you will have df over dxi as the derivative of the objective function, but just only one mu I with a coefficient of -1, because the rest of them drops with 0 coefficient. So you get this equation. Since you have the complementary equation like that, you can write this one as -xi, which turns into mu I xi is equal to 0. You can drop the negative coefficient here. Original constraints, and also you can write that these are the non-negativity constraints in original. Of course, all the mu values will be greater than 0. So for considering these first order necessary condition, we search for points from 1 to 4 and treat these points as candidate extremizer. But we will simplify our ideas, simplify our form that we write here. Observe that from the first equation, transpose mu I to the right, and you will get mu I is equal to df over dxi. So you can say that since mu is equal to df over dxi, and we know that mu is greater than equal to 0, the classical first order necessary condition, our first condition becomes df over dxi is greater than equal to 0. This inequality tells you that in a constraint problem, if the variable that has a non-negative situation, you can write that dl over dxi. Of course, we are writing f here, but if we have some other constraints, it will be l. dl over dxi will be greater than equal to 0. Second, complementary conditions. What was that? It was like that. Complementary conditions. But we say that xi times mu I, instead of mu I, we are writing df over dxi or dl over dxi. More generally, you need to write L here, okay? Xi times dl over dxi is equal to 0. Again, this is complementary constraints, and xi is greater than equal to 0. So, we updated our first order necessary condition, as you see, not to include mu unknowns. So, which means that you decrease the total number of the unknowns in your system, in your phone system. So it's a good thing for you because in this case you will have n plus n equations to find n plus n unknowns, but without mu, you just have the xi variables here. You have just only n unknowns in this system. So it will be easier for you to get the result, okay? So lecture 3 actually simplifies the non-negativity conditions. Of course, we will apply the same idea. We will find the candidate points, satisfy 5 and 7. I mean, these equations, and we will apply the second order sufficient condition. Second order sufficient condition, this was the complementary, this was the first order condition equation, but it's written in vector form, as you see. We didn't write df over dxi minus mu I only. Why? Because this is the vectoral form, gradient f of x. So here mu I times a vector I. This is not identity. It's a vector in n by 1 because this actually will be in the same way. And you will get this one. So if you take the second order sufficient condition, nabla square L will be appear like that. Nabla square f of x will be appear like that. Since this part does not include any x, it will drop and nabla square L will be equal to nabla square f of x. So L and f have the same Hessian. So actually nabla square L and also mx star, the final matrix that we need to analyze for definiteness will be the same. For the second order sufficient condition, we again state the same. Nabla square L x star mu with respect to x only. So the dimension will be n by n here. Is positive definite over the feasible region set. Then it will be strict minimizer and you can consider the other combinations. So I'm copying the Can you see my screen, guys? I think I shared only the PowerPoint file. It will be better to... This is the problem we will do. Let me write. Let me begin. First of all, I learned something last week. Where is it? I found a full screen mode. Not this one. Maybe... Where it is? I couldn't see. Oh, it's here. So it will be better to see the complete page. Anyway, minimum f of x, y, z, it's a three variable function. All the variables is greater than 0. Of course, without applying the third title, you are free to write your Lagrangian as your f plus lambda 1 times minus x plus not lambda. Lambda is not a good choice because we say that Karışkan-Tucker conditions with mu conditions. Mu 1 time minus y plus mu 3 times minus z. But this is long because we have three unknowns. Instead of this, we will apply title 3, and we write that our Lagrangian will be written as you see, here, f of x function, 2x squared plus 3y squared plus z squared minus 2xy plus 2xz minus 2x minus 4z. I'm not just adding the mu1 parts, just I will solve them directly by considering the idea that we discussed in title 3. First order necessary condition. What is that? dl over dx. What is it? 4x minus 2y plus 2z minus 2. I know that. If x is a free variable, I will write it equal to 0. But since it is greater than equal to, it must be greater than equal to 0. I didn't write the equality. It is greater than equal to 0 that I discussed in the title 3. And also, of course, by this way, I can use the left part. And also, x times dl over dx, which is my complementary condition. X times 4x minus 2y plus 2z minus 2 is equal to 0. Similar to that, dl over dy is equal to 6y minus 2x, that's all, is greater than equal to 0 because y is greater than equal to 0. And similarly, y times dl over dy, which is y times 6y minus 2x is equal to 0, okay? And dl over dz is equal to 2z plus 2x minus 4 will be greater than equal to 0 since my z is greater than equal to 0, and consequently I need to write the complementary constraints like that, okay? This is the thing you need to do if one of the variable is greater than equal to 0. If, for example, y is not greater than equal to 0, then you have to write this is equal to 0 and you don't need to write this one, okay? You don't need to write this one. So based on the non-negativity variable, we will write these conditions. Anyway, after that, of course, we will consider that there's no other condition, so we only need to consider other x, y, and z is greater than equal to 0, which is our original constraints already. This is our first order necessary condition. So in our first order necessary condition, I will find some candidate points. Of course, to find some candidate points, I need to use the equalities, not inequalities. Of course, I will consider the inequalities to check that my finding candidate point is just really candidate or not. But we need to focus on the equality that we write here. Okay, so say that, name this condition as 1, 2, 3, 4, 5, 6, and say that these three both are all of them are 7. So it is obvious that you will use the constraints 2, 4, and 6. How you can use them? Of course, by multiplying them as 4x squared minus 2yx. It will be really complicated. What we do in complementary constraints is, I know that there are two factors here. One factor, the other factor. If two factors are equal to 0, then there are two options. X is 0 or the other is 0. We will analyze this one if we have complementary conditions based on x is 0 or x is not 0. And y is 0 or y is not 0. And z is 0, z is not 0. So there will be actually 2 times 2 times 2, 8 cases that we need to analyze. So I will begin by, for the 8 cases. First case, I will assume that all of the variables are 0 And we will analyze each case to find a candidate point. So this is the thing what we do in complementary constraints, and we apply the same idea actually. So if all of them are 0, then I can say that 2, 4, and also the constraint 6 satisfy directly. I don't need to check them because these are the factor already. So I need to check the remainings. What about 1? 1 is satisfied with 0, 0, 0 value. This is a point. This is a candidate point, maybe. I'm not saying candidate, but substitute this one into 1. 1 is here, as you see, 0, 0, 0, but minus 2 is not equal to 0. So you put a cross out there, which means that no point is obtained from this case, okay? No point. And after that, second, we will begin by x is different from 0, but the rest of them 0. Okay? Rest of them 0. So if x is different from 0, first of all, you need to consider the corresponding complementary constraints. If this one is different from 0, then this part must be equal to 0. By considering y and z is 0, it will be 4x minus 2 is 0 directly. Okay? 4x minus 2 is 0, so x is half. Y is 0, z is 0. You found the point, but I'm not saying it's candidate. I need to check the inequalities. I'm checking the 1. Is it necessary to check 1? No. You already use 1 to find your x, so 1 is already satisfied. You don't need to check it. But what about 3? I'm checking the 3. 6y minus 2x. 6 times y minus 2 times x must be greater than equal to 0. I'm checking it, so cross out, no point there. Third, I'm checking that x is 0, y is different from 0, z is 0. So if y is different from 0, the derivative with respect to y, which is 6y minus 2x, must be different from 0. I'm writing 6y minus 2x must be 0. It tells me that if x is 0, then y result in 0 also. So again, you assume that y is different from 0, but you didn't reach a point that has a positive y value. Fourth, x is 0, y is 0, but z is different from 0. If z is different from 0, 2z plus 2x minus 4 is 0. Since x is 0 here, 2z minus 4 is equal to 0. Let me write 2z minus 4. 2z minus 4 is 0, which tells me z is 2. X is 0, y is 0. I will check all of them. I will check 1 first. Let me take the photo of the above. Okay. I will describe by the number of the constraints, okay? I don't want to go up and down. For the first constraint, it was 4x minus 2y plus 2z minus 2 is greater than equal to 0 or not. X drops because it is 0, y drops because it is 0. I'm checking that 2 times 2 minus 2 is greater than, yes, it's satisfied for the first. Let me check 3. Third equation, third inequality actually. It was 6y minus 2x is greater than equal to 0. It is 0 greater than equal to 0. It is satisfied. Let me check 5. Is it necessary to check 5? No, because 5, actually we assume this part is 0. This part is 0 means that this is satisfied already. So this is satisfied already. So by considering all 1 to 6, you found a candidate point, guys. Your candidate point xyz is equal to 0, 0, 2. You found 1, okay, from the fourth case. Anyway, let's continue. We will get, this was the fourth cases. Fifth case, um, we consider one of the variables is different from zero. Now I will consider both. X is different from zero and Y is different from zero while Z is zero only. Okay? If X is different from zero, then the equation, the inequality is 1 will be satisfied as equality 0 and similar for that. So I'm writing it 4x minus 2y. I'm not writing 2z because z is 0. Minus 2 is equal to 0. This is the parentheses that we need to equalize to 0. And the second one, the third, 6y minus 2x is 0. Yes, that's enough. So as you see, two unknown, two equations. So it's easy for you to solve it. X is equal to 3y. Substitute in the first. 12y minus 2y is equal to 2. 10y is equal to 2, y is equal to 1 over 5, x is equal to 3 over 5, z is equal to 0. Maybe I found a candidate point, but what I need to do is I need to check the inequalities. This point must satisfy all the equalities and inequalities that I write above, okay? I don't need to check 1. 1 is automatically satisfied. 3 is automatically satisfied, but I need to check 5. Okay, I need to check 5. What is 5? Let me write. 5 is 2z. Actually, no necessary to write z because it is 0. 2x minus 4 is greater than equal to 0 or not. Let me check. This is 0. It drops. 2 times 3 over 5 minus 4 is greater than equal to 0 or not. 6 over 5, no. It does not satisfy. The part here, it's a negative thing. I didn't calculate, but it's negative. Negative cannot be greater than 0, so no point, okay? No candidate point. So this point is not a candidate, okay? Not a candidate. Because it doesn't satisfy the fifth inequality. It is enough to eliminate the corresponding point if at least one of them is not satisfied. Anyway, this was the case 5, now case 6. We assume x and y, now we assume x, and also z is different from 0 while y is 0 here. If x is different from 0, let me write, I'm considering 1, and 4x, I'm not writing y because it is 0, plus 2z minus 2 is 0. And for z, 2z plus 2x minus 4 is 0, okay? This is from here, and this is from there. So I need to solve z and x. Let me write a simpler form. 2x plus z is 1. Z plus x is 2. Minus minus minus. X is equal to minus 1. We already know that x is greater than equal to 0 constraint appear in my problem. So I'm just crossing out there. No point comes from these cases. Okay, this case. Anyway, next. Here, the 7th case. I will analyze in 8th position. By the way, in the final exam, as you know, you are really crowded. You are 200 and something. So I did my midterms in the multiple choice form. But this part, I think, is not suitable for multiple choice question. In the final exam, you will have one open-ended question, okay? Open-ended. Of course, you will have some multiple choice questions like the midterms, but you will have also one open-ended questions. So you need to do this analysis one by one like I did in the class, okay? I hope it's clear for you. Final exam will not be completely multiple choice. I think in this way now, maybe I can change my mind, but I advise you to get ready for different types of question, okay? Maybe open-ended, blank parts. I don't know how to do this. I didn't discuss with my brain, with myself. But probably you will have one open-ended question in the final exam, okay? Anyway, I analyze x and y different from 0, x and z. So x is 0, y is different from 0, and z is different from 0. If y is different from 0, then 6y minus 2x is 0. Oh, it contradicts. If x is 0, then y will be 0 by this equality, so no point from there. I finished the analysis. So our final and the hardest part, I think, we will assume that all of them will be different from 0, which means that if x is different from 0, we will write 4x minus 2y plus 2z is equal to 2. If y is different from 0, 6y minus 2x is 0. And if z is different from 0, 2z minus, not minus, plus 2x minus 4 is 0. So you have to solve this system of linear equations. 3 equations, 3 unknowns. I think it will be easy. Use the second and write x is 3y and rewrite the equation 16 and 10y. 10y plus 2z is equal to 2 as the first. I use the second. 2z plus 2x, not 2x, 6y is equal to 4. Okay, I need to solve z and y here, so I can find my x directly by using the equality, by using the relation for x and y. Here, let me write with the color, minus, 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 so I'm adding them up, then 4y is equal to minus 2, cross out. So no point from the final case, 8 case, okay? So anyway, what we did here is, actually, again, we write the first order necessary conditions. We will find some candidate points that satisfy 1 to 7. To do this, we focus on, again, like we did in the previous titles, complementary constraints that are equal to 0 or not. Because, of course, you don't have to do this analysis. Maybe you can multiply it and you can use some methods that solves nonlinear equation system, because these will be nonlinear, as you see. But it's hard for us. For our class, all you need to do is analyze these first order necessary condition to find candidates by focusing on the complementary solutions. Of course, since I write 8 cases, if you analyze just 5 cases or less, or some other than 8, then you didn't analyze all the cases, so you will be wrong. There will be missing points in the exam, I mean, okay? So you have to analyze all the cases that we discuss here. Anyway, we found one candidate point. There is no other. It was 002. Remember that your candidate point 002 satisfy all these 7 equality and inequalities conditions, I mean. So I'm ready to write my second order sufficient condition. For that, I need to write nabla square Lxx. What does it mean? I'm considering the Lagrange, but just taking the derivative with respect to x vector or xyz variables, okay? xyz variables. This is the x vector, not only simply x. So I have 3 variables, so I will write that 3 by 3 matrix Hessian, okay? For example, I will focus on the first derivative. I will focus on this one and take the derivative with respect to x. It will be 4. It will be minus 2 with respect to y, and it will be 2 for the z. So second row, minus 2, 6, and 0. Third row, 2, 0, and 2. Okay? 2, 0, and 2. Let me write it here. 4 minus 2, I don't remember, 2. The second one, with respect to x, is minus 2. With respect to y, it is 6. It is 0 here. For the final one, it is 2 here. No y. And z, it is 2. Okay? So we need to analyze, actually, definiteness of nabla square Lxx. Okay? As you see, there is no variable in your Nabla square L. Of course, we have a candidate point as 002. If there are some variables there, of course, I will substitute it, but there is no, so it is constant. So I'm writing my LPMs. Delta 1 is 4, greater than 0. Delta 2 is 24 minus 4, greater than 0. Delta 3 is, let me focus on the final row and expand my determinant. 2 times third one, so it is minus 2, 2, 6, and 0 plus 0 drops 2. Again, it will be positive because third, so 3, 3 plus an even number. There is no minus 1 to the 4 minus 2 and 6. So 2 times 0 minus 12 plus 2 times 21 minus 4. Let me do the operation. 2 times minus 2 minus 24 plus 2 times not 20. So anyway, it is greater than 0. So we are lucky. It is positive definite. Okay, it's positive. If it is positive, my candidate point 002 is a strict minimizer or just a minimizer, local minimizer. Okay. Anyway, do you have any question? Finish the. Where is the chat? Okay, you don't have any question. Let me continue with my next question. I think this will be here. In our previous example, all the inequalities are non-negativity, so it was simple to do the analysis, but this is not the case all the time. If you have a general question like that, where is the full screen mode? Yes, it's here. So I will write that my Lagrangian is equal to, it's okay to write like that, f of x plus lambda. I will relate this one with lambda, this one with mu, and I will cover this one with title 3. So I will not write mu1, mu2, mu3, and mu4. You can do that, but it's really complicated. Lambda times x1 plus x2 plus x3 minus 2 plus mu times minus x1 plus 2x2 2x2 sorry, I'm thinking something minus 3. That's all. So I'm ready to write my first order necessary condition. I'm writing that dl over dx1 is equal to 2x1 plus x2 minus 6 plus lambda minus mu. Since it's greater than equal to 0, it is greater than equal to 0, but x1 times dl over dx1, which is x1, 2x1 plus x2 minus 6 plus lambda plus mu is equal to 0. dl over dx2 is x1, 4x2 minus 14 plus lambda plus 2 mu, 2 mu is greater than equal to 0 since my x2 is greater than equal to 0. And also x2 times this Oh, our objective function doesn't include any x3. It's interesting. 0 from the objective function. And what about the constraint? It is lambda. Just lambda. Lambda greater than equal to 0. x3 times lambda is 0. Nice. Okay then. Of course, these are the first type, and also I need to consider if in the exam, if I ask write the first order necessary condition for the problem, then you have to write all the things, okay? These 6-1, and also you need to consider that my original constraint must be satisfied also. Minus x1 minus 2x2 is less than equal to 3. Second inequality. For inequality also I have the complementary constraints. This one. And also my mu is greater than equal to 0. And also my x1 greater than equal to 0. x2 is greater than equal to 0 and x3. Is there any other? Let me check. For non-negativity, I write first derivative greater than equal to 0. The variable times the first derivative is 0. For 3 of them, I did the same. My original constraints, there is no extra constraint for my equality type, but extra constraints, extra complementary constraints is required for inequality constraint. I write it mu times. And I write my non-negativity. This is the answer. If I ask you in the exam, write the first order necessary condition. If you didn't write non-negativity, you will not get full score. If you didn't write complementary, you will take partial credit, okay? Be aware of this. Anyway, we will focus on the equalities again. 1, 2, 3, 4, and 5. These yellow equalities will help us to find the candidate points. Of course, the final point that we found will be checked by the others. Okay, I mean inequalities. 1, 3, 5, 2, 4, 6. Say that this is 7, 8, 9. All of the inequalities, nonlinear inequalities, non-negativity constraints is 10. So what you need to do is, again, x1 based on 0 or not. Some of the constraints will change. These are the complementary constraints that I showed by is yellow. Just only out of 7. All of them are complementary. So I will investigate x1, x2, x3, 0 or not, 8 cases. And also I can do this analysis in a subcase. Also, sometimes it is necessary. I will investigate the mu's. So again, 8 cases for 0 or different from 0 for x1, x2, and x3. So let me begin. If there is no x, y, z here, these are x1, x2, and x3. If x1 is 0, 2, 4, 6 satisfy directly. Focus on 7th equation. 7th equation tells me that 0 plus 0 plus 0 is equal to 2. So cross out no point. 2i. Say that x1 is different from 0 while the remainings are 0. Then, if x1 is different from 0, then from the complementary constraints, I will write it 2x1 plus x2, x2 is 0 already, I'm not writing, minus 6 plus lambda minus mu is equal to 0. Okay? And let me check. From 7, since both of them are 0, then x1 is 2. From 7, x1 is 2. And let me write the ninth equation. I don't know what will happen there. Mu times minus x1 minus 2 minus 3 is 0. Then it tells me that mu is 0. If mu is 0, then this becomes 4 minus 6 plus lambda minus 0 is 0. Then lambda is 2. I guess I found the point. Let me write x1, x2. I found all of them. x3, lambda, and mu, my candidate point. Let me check. 2, 0, 0, 2, and 0. Of course, I need to check the inequalities that satisfy with this or not. I don't want to check 1. 1 is automatically satisfied because I use 1 to do the calculation. 2, 4, and 6 already satisfied. What about 3? Let me check the third. x1 plus 0 minus 15 plus 2 plus 0 is greater than equal to 0 or not. It's obviously no point. Okay? It doesn't satisfy the third inequality. So I pass the next cases. Third. X is 0, but y is different from 0, but z is 0. If y is different from 0, what with y? Oh, why I'm writing like that? Oh, there is no y, there is no z. Drops because it is 0. So you get this one. Okay, then. There is no other. I'm focusing my equalities. 2, I cannot, 2 is satisfied already. I cannot write anything. 4, I write 4. 6 is satisfied already. 7. By the 7, x2 is equal to 2. Okay. And also for the 9, it is mu times minus x1, 0. 2x2, 4, minus 3 is 0. So it tells me that mu is 0. So substitute them into the first equation. 8 minus 14 plus lambda plus 0 is equal to 0. Lambda is equal to 6. Okay, then I found a point. 0, 2, 0, 6, and 0. Let me check. 1, should I need to check 1? Yes. 2x1 plus 2 minus 6 plus lambda minus mu is greater than equal to 0 or not. It's satisfied. What about 3? I don't need to check 3 because I use 3 as an equality here. 3 is automatically satisfied. I need to check 5. Lambda is greater than equal to 0. It is automatically satisfied here. 7 is satisfied. Let me check 8. Minus x1, 0, plus 4 is less than equal to 3. That's no point. Next case, fourth. X1 is different from, 0. Not different, it's 0. X2 is 0, but X3 is different from 0. Yes. If X3 is different from 0, the coefficient of it, which is lambda, has to be 0. Okay, because X3 times lambda is 0 from the sixth equation. If this is different from 0, this must be 0. If both of them 3 from 7, I can write x3 is 2. From 9, mu times 0, 0 minus 3 is 0, then mu is 0. I found a point, maybe. 0, 0, 3, 0, 0. Let me check. The first inequality, 0, 0 minus 6 plus 0 minus 0 is greater than equal to 0 or not. Cross out, no point. Next case. So we will assume x1 is different from 0, x2 is different from 0, but x3 is 0. If these two, if x2 is different from 0, then x1 plus 4x2 minus 14 plus lambda plus 2 mu is equal to 0. If x1 is 0, x1 is different from 0, 2x1 plus x2 minus 6 plus lambda plus mu is 0. Yes. 5. Okay, just consider the equalities. x1 plus x2 is 2. And mu times minus x1 plus 2x2 minus 3 is equal to 0. As you see, I write the updated equalities. These are the updated equalities, okay? Equalities. It is obvious that I cannot decide and solve these unknowns because I have one complementary here. So again, as subcases, subcase A, I will investigate mu is 0, and the other subcases, I will investigate mu is different from 0. If mu is 0, this is satisfied. And from this one, I can write x2 is equal to minus 2 minus x1. And I will rewrite the first equation, x1 plus 4, 2 minus x1 plus lambda. I write the 0 for mu is equal to 14, first equation, 2x1 plus x2, 2 minus x1, not minus, plus lambda is equal to 6. So I will solve these unknowns here. Let me do some arrangement. X1 minus 3x1 plus lambda. This is 8. This is 6. Let me check. X1 plus lambda is equal to 2 drops there, and it's 4. Minus 4x1 is equal to 2. x1 is equal to minus half. x1 must be greater than equal to 0, so I'm putting a cross out. No point comes from this sub case. I will investigate mu is different from 0. If mu is different from 0, then the coefficient, this parenthesis must be equal to 0. Minus x1, 2x2 is equal to 3. And also I know that x1 plus x2 is equal to 2. Add them up. Then x2 becomes 5 over 2. And x1 becomes 2 minus 5 over 2. Again, it is negative. Oh, schade. Let me check. 3, 5. Oh, 5 over 3, not 2. 3x2, 3x2 is equal to 5. It's 5 over 3. So it is 1 over 3. Yes, we found it. So I think we got a point. Let me write 1 over 3, 5 over 3, 0. But I don't know what is lambda and mu. I'm not ready to write my candidate. Let's pick up there. We will complete the missing part. I don't know what is lambda and mu, so I will use the original equation to find my lambda and mu. Mu is different from 0. Lambda, what is lambda? Is there any condition for lambda? No. From the first equation, I will write lambda plus 2 mu is something. What is that? Let me calculate. X1 is, what was that? I forget it. Let me copy the upper part here. I will use the first two to find my lambda and mu. One over 3 plus 7, 20 over 3 minus 14. This is 7. 7 minus 14 is minus 7. Transpose it to the right, it is 7. The next, lambda plus mu is equal to 2x1, 2 times 1 over 3 plus 5 over 3. It is 7 over 3 minus 6. 7 minus 18 over 3, which is 3. Transpose it to the right. It's this one. Okay. You need to solve for lambda and mu. Negative, negative, negative. Mu is equal to 7 minus this. 10 over 3. Lambda is equal to this 1 over 3, 1 over 3. So I'm ready to write my candidate, maybe candidate point. Lambda is 1 over 3, mu is 10 over 3. So this is my point that I found here, but I need to check the inequalities. Let me check them. One is automatically satisfied. I'm not checking 1. 2 is automatically satisfied. I'm not checking 2. 3, I need to check the, sorry, this is 1, this is 3, fifth. Fifth must be checked, which is lambda is greater than 0. It is satisfied. 2, 4, and 6 directly satisfied. 7 directly satisfied. I use 7. I didn't use 8. I need to check 8. Minus x1 plus 2x2 less than equal to 3 or not. It is, yes, it's an active constraint. It's satisfied. 8. 9 is already satisfied. Yes. This is a candidate point, guys. Candidate point. Okay? Because it satisfies all the equality and inequalities in my problem. So this was the fifth case. Fifth. Now I will write sixth case. Case 6. What was case 6? I forget it. If x1 is different from 0, I'm writing that 2x1 minus 6 plus lambda plus mu is equal to 0. If x3 is different from 0, then lambda have to be 0. So it becomes 2x1 minus 6 plus mu is equal to 0. Lambda is 0. I'm checking that. I just use two inequalities here. Fourth is satisfied directly. 7. From 7, I can write x1 plus x3 is 2. From 7, I write it. From 9, I can write mu times minus x1 plus 2x2. There is no 2x2 because it is 0. Minus 3 is equal to 0. I write the equalities there. Let me check the general whole idea. So again, I will do sub-analysis. If mu is 0, then x1 is 3. If x1 is 3, then x3 is minus 1, so no point. B, if mu is different from 0, then this part must be 0, which shows me that x1 is minus 3, no point. So go to next case. Case 8. X1 is 0, but x2 is different from 0, and x3 is different from 0. If x2 is different from 0, then I'm writing that 4x2 minus 14 plus lambda plus 2 mu is equal to 0, have to be 0. For x3, then lambda have to be 0, so this lambda drops there, okay? And by the way, x2 from the 7, x2 plus x3 will be 2 from 7. From 9, let me write mu times x1 0, 2x2 minus 3 is 0. 2x2 minus 3 is 0. These are the things that I need to do. Again, sub-analysis, I think, because I have x2, x3. I have 3 unknowns, but 2 equality. I'm dropping the complementary. I cannot use it directly, so sub-analysis is necessary. Mu is 0, then my x2 is 7 from this equation. If x2 is 7, then my x3 is minus 5, cross out. If mu is different from 0, then 2x2 minus 3 is equal to 0, which means that it is 3 over 2. Then x3 is 1 over 2. Nice. Find mu. 4 times x2 minus 14 plus 2 mu is equal to 0. Then it is 6 minus 8, 8, and mu is 4. I think I got a candidate, another candidate point. x1 is 0, x2 is 3 over 2, x3 is 1 over 2, lambda is, what is lambda? Lambda is 0, and mu is 4. I will check the equalities. I need to check one, but I didn't I use it in equality. No, I need to check one. I'm checking one. 0 plus x2 minus 6 plus lambda minus mu is greater than equal to 0 or not. It is obvious that it's not satisfied, guys. It is negative. It's not a candidate point. I think that I found a candidate point, another candidate point, but it's not. As you see, it doesn't satisfy it. Okay, cross out. So this case is over again. No point comes from this case. Final case. Case 8. x1, x2, and also x3 is different from 0. So I need to write 2x1. It will be hard for us. x2 plus lambda plus mu is equal to 6 from 2, from 4, x1 plus 4x2 plus lambda plus 2 mu is equal to 14. And from the third, lambda is 0. We're lucky. We get a simple thing. From 6, lambda have to be 0. Um, Again, from 7, I'm not dropping any of the variables. The summation is 2. But also I have another complementary minus x1 plus 2x2 minus 3 is 0. I don't have any other equality. I write these two to this one. So I need to do a sub-analysis again. A is mu is 0. If mu is 0, the first one is 2x1 plus x2 is 6. Lambda is 0, so I'm dropping lambda, guys, okay? These are zeros. And the next one, x1 plus 4x2 is 14. Minus 2 times the second, minus 2x1, minus 8x2 is equal to minus this. I'm adding these two up. Minus 6x2, not 6, 7. Minus 7x2 is equal to minus this. x2 is this. What is x1? x1 is 1 over 2 times 6 minus 22 over 7. It is 1 over 2 times 42 eksi 22, 20 bölü 7. So it is 10 over 7. x1 is 10 over 7. And x3 is, the summation of them is 2 minus 22, 10, this. Oh, we are lucky. It's negative. So no point. Okay, I finished. The next one, mu is different from 0. If mu is different from 0, then the complementary condition tells you that minus x1 plus 2x2 is equal to 3 by the complementary. And by the way, lambda is 0, it drops. I need to write these equations again. I couldn't see the big picture. So let me write 2x1 plus x2, lambda is 0 plus, not plus, minus mu. Oh, minus mu is equal to 6. The first, why I write this one? Sorry. Oh, yes, we assume all of them are different from 0, so I'm focusing on 2 and write that 2x1, x2 plus, it is plus mu or negative? Oh, guys, I found a mistake. Oh, at the beginning of the question, I'm sorry. As you see, guys, it is minus mu, but I write it as lambda plus mu. It is wrong. This is my mistake. I have to write lambda minus. Sorry, everything will change, maybe. I don't know. So I'm just stopping my case analysis. I think you got the point. I don't want to redo all the time, all of them. Okay, maybe I can check only my candidate point is satisfied or not. What is my candidate point? It's candidate point 1 over 3, 5 over 3, 0, 1 over 3, and 10 over 3. But I use this one is satisfied, so there's Again, it will satisfy by all the inequalities. Let me focus on the second order. I'm stopping this one and lefting the final cases. Sorry. Here. I didn't finish the final cases. You need to do that. Okay, this is homework. But I know that there will be no other candidate points. Okay, I remember like that. Maybe it is. You can analyze the other candidate point that you found here. But this is homework, the rest of them. All the cases will be done here. So second order sufficient condition can be written. Nabla square LXX. Let me write it. I'm focusing on the first order necessary condition. It will be 3 by 3. 2, 1, 0. The second one, 1, 4, 0. The third one, 0, 0, and 0. So it is obvious that it's not definite. Let me write. Nabla square LXX is neither positive nor negative. How I decided this? Since delta 3 third LPM is 0 directly because I have a 0 row and 0 column. So I need to analyze positive semi-definiteness. Yeah, or positive or negative. Semi-definiteness must be checked. Definiteness must be checked. Okay, positive or negative, I don't know. Let me check. First order means that I need to write PMs, okay? First order PMs, 2, 4, and 0. Second order, 2, 1, 1, 4. 2, 0, 0, 0. Close out, close out. And 4, 0, 0, 0. And calculate them. This is positive. This is 0. This is 0. Okay. Third order PM is 0 directly, so I can write that. I can conclude that Nabla square LXX is positive semi-definite. Semi-definite means that Nabla square is positive semi-definite over Rn, which means that it is also positive semi-definite over Hx star, feasible direction set. So no need to construct Hx star. So the candidate point is a minimizer. That's all, guys. Okay. Oof. I want to show one extra question to you because I think, I don't remember exactly, but I didn't analyze the feasible direction set construction is required question. Okay. So I will not do the step by step, but I will show you Hx star. So if the question is, we will analyze one more question, but I will not write. I already solved it before my previous classes. The question is, f of x is equal to x1, x2, 2x, 2x3, 3x1, x3. And the condition is just only one equality, no Cantucker but Lagrange. x1, x2, x3 is 3. Summation of them is 3. So question is, classify each extremizer as local maximum, minimum, or saddle point. This is our Lagrange condition, Lagrange problem. This is our function f. And this is lambda times the equality constraint. First order necessary condition, the derivative with respect to x1, derivative with respect to x2, x3 is 0. And we have one equality constraint. It's a Lagrange problem. It's an easy one. It is title 1. our title 1, I mean. So by considering the equality 1 to 4, we need to search for 4 candidate points. So if we equalize 1 to 2, you will get something. You can do the math. So there's recording from there. Anyway, you found a candidate point 3 over 2, 0, 3 over 2 from 1 to 4. Okay, you did the analysis and you find for a candidate point. For the second order sufficient condition, you will write Nabla square LXX. You have 3 variables, so the dimension will be 3 by 3. You write this one. You need to analyze the definiteness. You begin with LPM, but you face with a 0 main principal minor. So which means that you need to go for PMs because there is no possibility for positive or negative in this situation. For PMs, you write first order as 0, 0, 0. You for second order, you write this one. So the first one is -1, the second one is -2. So we say that for positive semi-definiteness, all of the orders, first, second, third, all of them will be 0 or positive. For negative semi-definiteness, first order begins with negative or 0, but the second order goes for 0 or positive. So there is no possibility for the matrix Nabla square L to be definite. So we conclude that it is indefinite, which means that it is indefinite over Rn. Since it is indefinite over Rn, which means that actually it is also indefinite over the feasible set. So without writing the feasible direction set, you cannot decide the definiteness. So in this situation, you have to write your feasible direction set. Okay, this is the reason I'm showing this question. Okay, maybe I solved it before, I don't remember, but let me emphasize it again. So what we need to do is, we need to analyze Nabla square L is indefinite over the feasible direction set. How to write feasible direction set? We need to write the active constraints. There is only one equality constraint. It is automatically active. So I just considered the function g, constraint g here. So what is the gradient g? Gradient g is derivative with respect to x1, x2, and x3. So it is 1, 1, 1. So the feasible direction set tx star, or maybe we write hx star, I don't know, the same. It includes h in r cube, which means that the vectors h1, h2, and h3, the gradient of the constraint transpose times the h vector will be 0. This is the feasible direction set for this question. You need to consider all active constraint in this step, okay? All active constraint in this step. Anyway, if you do that, 1, 1, 1 times h1, h2, h3 is 0, or simply h1, h2, h3 is 0, which is your constraint. You are going with the direction of your constraint actually here, okay? So we will consider the vectors such that, for example, of course, 1, 2, and -3, as you see it them up, they add up to 0. Anyway, so we need to do the sign analysis for H transpose Nabla square LXH by this condition. Instead of H3, I will write -H1 minus H2 by combining to our condition. So we write this is H, this is Nabla square LX, X, this is another H transpose. So we did this multiplication. Of course, you need to do the algebra. You just need to multiply both of them. And anyway, our idea is to analyze the sign of this multiplication, sign of the function that depends on h1 and h2. And we need to write the actually complete square of them. If you write the complete square form, there is a negative here and there is complete squares form. We decided that it is always greater than 0. Actually, there is no possibility for greater than equal to, because both of them, all of them cannot be 0 directly. So anyway, we decide that the feasible direction set is always negative, which means that it is negative definite over the feasible region set. So your candidate point will be a maximizer by this analysis, okay? By these analyses. And that's all, guys. We finished our term. I finished all the topics. Let me write again. Write again. Your makeup exam. Your makeup exam will be on this date. I will be on this date. I don't know the classroom. What was the R? What was I write? Did I write? I think it is 10:30. I write 10:30? 10 or 10:30. I don't remember. I will announce by email, of course, when I get the classroom information from our department, okay? If we crowded, we need to do something. Maybe if I couldn't any classroom find, then our exam, our midterm exam can be at 1. I don't know the hour, okay? I will inform you. But your makeup exam will be next Monday. So the term is over. Actually, to be honest, I didn't like the optimization course this week. This term, not this week. Not this is the week case. Uh, because I feel very alone. You didn't attend my classes. You have the recordings, so I didn't like this style. But this is the case. I couldn't do anything. Since you are a crowded class, then I have to prepare some multiple choice question. But your actually grades are really good. I hope you didn't cheat. Uh, I couldn't contact with you in this class, so it's actually a little bit hard for me. Anyway, the term is over. I hope you will graduate it. You will have your final exam probably with one open-ended question. Okay, one open-ended question for final exam. You're crowded, but I will do that for the final topic, of course. I need to do that. I will be patient and evaluate all of them. All the topics covered will be content of the makeup exam, final exam, resit of the final, makeup of the final, bütünleme I mean. Then that's all. You are just one class. Of course, I will, I don't know. I didn't say you anything about the curve. Maybe I can use the grade scale of the university directly. I don't know. We will discuss them later, okay? I will think about it. Okay, then take care of yourself. Bye bye. Ben teşekkür ederim Azra. Mesaj yazmış olmam bile çok değerli. I hope you will graduate and you will have good lives, okay? Do not forget improving yourself. It's really important. Of course, we are not good enough, maybe in some subject, but try to do your best, okay? Take care. Bye bye.